Today in this video, we will configure MPLS Inter-AS VPN Option-C. It is the third option for interconnecting multi-AS backbones and the most scalable option of the three so far. One MPLS VPN v4 session transports all VPN routes or external routes between PE or route reflector routers. To simulate in our network, customer router 1 should reach customer router 2 through VRF black and brown. In the previous videos of this series, both customers can already reach each other globally. Now, we will separate the traffic using VRF. In our service provider network, in Option-C, customer router 1 is advertising an IP packet, then transit through ISP1 and ISP2, treated as one MPLS network, but in reality, it traverses in multiple autonomous systems until it reaches its destination, which is customer router 2. The same process on the reverse traffic from customer router 2 to customer router 1. Customer router 1 and customer router 2 advertise their routes to their respective PE routers. The PE routers will redistribute those routes if learned from other protocols other than BGP. Those routes will retain in the route reflector routers. Then each route reflector will establish multi-hop eBGP VPN v4 to transport and exchange those routes. For the route reflectors to reach each other, the routes or loopback interface addresses learned from IGP will be advertised by the ASBR routers. Both the ASBR routers will establish an eBGP IPv4 neighborship. Then, the ASBR routers will redistribute those routes from BGP to IGP. Let us go back to our task. To achieve this, follow the steps below. Some configurations were already done in the previous videos for PE to CE VRF communications and route redistributions. In ISP1 and ISP2, both OSPF and eBGP adjacency were already established. For VRF brown, eBGP protocol is used while OSPF for VRF black. Since we are done with steps 1 to 3, let us verify the routing table of each router before we proceed. Both XE Router 1 and XE Router 2 are receiving the route from customer router 1. XE Router 3 also received the route through BGP in VRF brown, while via redistribution from OSPF in VRF black. In XE Router 3, we can see in its routing table the prefix advertised by customer router 1 separated by VRF based on the route distinguisher. For VRF black, the route distinguisher is 1:21, while 1:11 for VRF brown. The same verification in ISP2 facing customer router 2. Both XR Router 4 and XR Router 5 receive the route from customer Router 2. In XR Router 3, only the BGP routes for VRF Brown is received. The route distinguisher for VRF Brown in ISP2 is 2:45, and no redistribution is needed if it is learned via BGP. Let us conduct redistribution in XR Router 4 and XR Router 5 for VRF Black. In XR Router 4, redistribute OSPF to BGP, then BGP to OSPF in VRF Black. Enter the OSPF process for VRF Black, then under VRF Black redistribute the BGP protocol. Next, enter BGP configuration, then under VRF Black redistribute the OSPF process. We have an error. In XR routers, the route distinguisher is configured under the VRF, but in BGP configuration mode. Enter BGP configuration again, then under VRF Black, input the route distinguisher, which is 2:54. The same configuration in XR Router 5. Now let us verify the receive routes in XR Router 3. XR Router 3 now receives the route from customer Router 2 for both VRF Brown and Black. Both customer routes are now received on the route reflector routers of ISP1 and ISP2. Step number 5 is also pre-configured in the previous video for IPv4 global adjacency between ISP1 and ISP2. Now let us proceed to step number 6. In XE Router 4, use network statement to advertise the loopback of XE Router 1 to XE Router 3 into global BGP. eBGP between XE Router 4 and XR Router 1 is already established and can receive each customer's prefix globally. In XE Router 4, enter BGP, then an address family IPv4, advertise the prefixes of XE Router 1 to XE Router 3 through network statement. In XR Router 1, use network statement to advertise the loopback of XR Router 3 to XR Router 5 into global BGP. Now let us check both the PE routers if they can now receive the prefixes. XR Router 1 now receives the loopback of XE Router 1 to XE Router 3, while XE Router 4 also received the loopback of XR Router 3 to XR Router 5. Both XE Router 4 and XR Router 1 now receive the prefixes. For the route reflectors to reach each other, redistribute the route receive in BGP on both XE Router 4 and XR Router 1 to their respective IGPs. Create a route policy in XR Router 1, then redistribute the route received in BGP from XE Router 4 to ISIS. Both route reflectors can't receive those prefixes yet. Let us start in XR Router 1, then redistribute the prefixes received from XE Router 4 to ISIS. Create a new route policy, then match the loopback of XE Router 1 to XE Router 3. Enter router ISIS, then redistribute BGP followed by the route policy. Create a route map in XE Router 4, then redistribute the route received in BGP from XR Router 1 to OSPF. After creating a route map permitting the loopback address of XR Router 3 to XR Router 5 of ISP2, enter OSPF configuration, then redistribute BGP and apply the route map created. Now, let us check the route reflectors. Both routers can now reach each other. Let us proceed and configure VPN v4 between XE Router 3 and XR Router 3. In XE Router 3, establish new eBGP neighborship to XR Router 3. Under BGP configuration, activate VPN v4 address family. Then add new BGP neighbor, which is XR Router 3. Activate eBGP multi-hop since they are not directly connected. Under VPN v4 address family, set the next hop unchanged. This feature allows BGP to send an update to an eBGP multi-hop peer with the next hop attribute unchanged. The same configuration in XR Router 3. Establish eBGP neighborship to XE Router 3, then activate VPN v4. Enable eBGP multi-hop, then set the next hop unchanged. Apply a route policy and allow routes to be sent and received. After VPN v4 configuration, let us verify the BGP neighborship and routing table on both route reflector routers. Both routers can now receive the routes from the customer both in VRF brown and black. Let us jump to our PE routers and verify the routing table. The PE routers in both ISP can't receive the routes from the customers. Now, configure the PE routers to import the routes that are exported by each of them in each VRF. XR Router 4 is exporting the route target 2:54 for VRF black, while 2:45 for VRF brown. The same route target values in XR Router 5. In XE Router 1, configure each VRF to import the route target exported by XR Router 4 and XR Router 5. The same configuration in XE Router 2. In XR Router 4 and XR Router 5, import the routes that are exported by XE Router 1 and XE Router 2 in VRF brown and black. For VRF black, the route target value exported by XE Router 1 and XE Router 2 is 1:21. While 1:11 for VRF brown. The same configuration in XR Router 5. Let us go back to the PE routers and check the VPN v4 routes in the routing table. XE Router 1 and XE Router 2 now receive the routes from customer router through XR Router 4, based on the route distinguisher for VRF brown and black. The same status in XR Router 4 and XR Router 5. All the PE routers can now receive the routes from each customer. Lastly, let us check the customer routers if they can receive each other's route. Customer Router 1 and Customer Router 2 can now receive each other's route in VRF brown and black. Now, let us conduct ping and traceroute for reachability testing. As we can see, ping and trace route from Customer Router 2 is not successful. The result is expected. Let us check XE Router 1 and XR Router 4 if they are receiving labels. Labels must be received on both routers and on the other PE routers for the connectivity to become successful. As we can see, there are no labels coming from the opposite PE router in XE Router 1 and in XR Router 4. Let us continue the steps to complete our task. In the ASBR routers, which are XE Router 4 and XR Router 1, configure Send Label under BGP facing each other since the transport label is broken, in this part due to MPLS is not activated on the link. In XE Router 4, enter BGP configuration, then enable the Send Label command facing XR Router 1. In XR Router 1, under BGP configuration, remove the existing address family for IPv4, then replace by address family IPv4 labeled unicast. Do not forget to configure Allocate Label all under Global BGP. Here, we will instruct the router to allocate labels on this routes under BGP that are advertised. In XE Router 4, let us check the interface facing XR Router 1 if MPLS BGP forwarding is now enabled. If not, manually enable it on the interface. As we can see, it is automatically enabled. Go back to XE Router 1 and XR Router 4 to verify the labels if already exchanged on the PE routers. Still, the PE routers are not receiving those VPN v4 labels yet, but can already be seen on the label forwarding information base of LFIB database. Let us proceed with our task. In step number 13, create a static route in XR router 1 facing XE router 4, since the network between them is a /24. XR routers will not generate label if the network is not /32. Enter router static, then under address family IPv4 unicast, create a static route towards the next hop IP in /32 network, followed by the exit interface in XR router 1. As we can see, in XE router 1 and XR router 4, BGP VPN v4 labels are already received. Before we proceed with the reachability testing from customer router 1 and customer router 2, let me show you the added prefixes on our LDP filtering on both ISP1 and ISP2. This steps is needed for those labels to be allowed and accepted on both ISP2. In steps number 14 and 15, the loopback IP address of the MPLS running routers are allowed in LDP filtering on both ISPs. Now, let us go back to the customer routers and conduct ping and tracer route. Both customers can now reach each other based on the ping and tracer route in each VRF. With this, our task for Inter-AS Option-C is successful. Refer to the configuration script on the screen for the commands that we have used per item in this task. I hope that this is informative to you and thank you for watching.